Okay, friendos, on to chapter 3. This is some short notes, hooray, but they are kind of important to what is coming up in chapter 3 and kind of answer some of our questions about how to find a determinant of something bigger than 3 by 3. So one of the most important things we need for this chapter is this notation. And if this is too small, it is the letters A, I, J. Okay, so I is going to stand for what row we are on, and yes, I can already hear the question. Why don't we just use A, M, N? Good question. Again, we're using I and J as counters, M and N being the total number of columns and rows and columns respectively. So we needed something that represented kind of what row we were going to be on, whereas M would be the total number of rows and N the total number of columns. So if we want to find out what Aij is, we're going to delete or eliminate the ith row and the jth column. So here I've asked you to find what matrix is A2, 3, which means we are deleting the second row and the third column. And we write down the matrix that's left. So I'm writing down 1, 9, 13, 2, 10, 14, and 4, 12, 16. Okay. This is going to be helpful notation for when we are going to start taking some determinants of smaller things. So for example, it was easy to find a determinant of a 2 by 2 matrix. And really, you could even break this up like we are going to later by thinking about this as A times the determinant of this 1 by 1 matrix, but the determinant of 1 by 1 is just that number. So A times the determinant of this, and then B times the determinant of this, and that's how we got AD minus BC. Okay, so determinant of 2 by 2. We've been using that for invertibility and all that kind of things. But in general, for any matrix greater than or equal to 2, the determinant is given by this here. We have chosen one, in this here, we've chosen one row to go across. So I'm sticking with row 1. So you can see this is A11 and then A12, which means I've moved over one column. And these are the entries. So this here is specifically A11, and this is A12, and this is A13. So it's that entry times the determinant of the matrix A11, which is the matrix that's created when we eliminate row 1 and column 1. That just start to feel familiar because that's exactly how we did the cross product in multivariable calculus, and how we're kind of been thinking about it in chapter 1 and 2 as well. Notice that it does alternate signs. So I want you to put a little star by that. It does alternate signs. And you could represent it as one big summation here if you wanted to. But often we're not going to do something big enough. You can also just compute it in your calculator. So we're not going to do something big enough to where you would need to really think about it as like a summation or anything really bigger than maybe 4 or 5 components. So let's try to look at what that meant here. So I'm just going to write this out, and you do not have to think about it this way, but the determinant of A is going to be A11, and we'll go across the top because I see a 0 here, and that would be really nice. So A11 times the determinant of A11, ooh, broken lid, oops, excuse me, and then minus A12 times the determinant of A12 plus A13 times the determinant of A13. Okay, so here A11 is the number 1, and then we are going to take the determinant, and this is our notation, I've written it down here. If I, instead of writing det, like DET of the matrix, I can just put 2 vertical lines around the matrix. They kind of serve as the brackets, but they are telling us to take the determinant of this matrix. So this will be the determinant of the small matrix once I've crossed out row 1 and column 1, -1, 0, 2, 1. Subtracting A12, which is 2, times the determinant of 3, 2, 2, 1, plus A13, which is 0, times, and I guess I'll write it, doesn't really matter, but the determinant of 3, 2, -1, 0. All right, and this is how we get our little formula. So I'm getting 1 times -1 minus 0 minus 2 times 3 minus 4 plus 0. So I've got -1 plus 2 equals 1. And that's my determinant. And hopefully you remember, as a side fact, that that means that this matrix is invertible because we got a determinant that is not 0. Okay, so let's go on to something more interesting, something that we know, because we already know how to do that, so that's fine. Okay, new definition. Okay, we're calling it the IJ cofactor. Okay, and that's going to describe, all right, well, maybe I will go back to the first sheet, but that's going to describe this alternating sign here and the determinant of AIJ. Okay. We're going to leave the components like little a11 to itself or whatever, and we're going to call this other component the cofactor. And that's going to help us later when we're going to start talking about making an inverse. We will need this definition, so don't forget about it. Cofactor. -1 I plus j, let me write this a little bigger, -1 I plus j times the determinant of AIJ. And if we want to find a determinant, okay, you can also write it, instead of writing determinant of A11 and having to remember your signs, you can also just go across. So this is, what they've written here is A1 C11 plus 2 C12 plus 0 C13, which is the determinant we took on the other side. This is just a useful way to kind of organize our alternating signs and the fact that we are going to then take the determinant of this. Okay. And we can do this actually either across the top or down the side. We can actually do it down any column or any row, which is super nice because sometimes we want to choose a different column or a different row, maybe one that has a lot of zeros in it, which would be really nice. This matrix of signs is here. I think it's just way easier to remember the actual, like, what number you're on, and you can put them into the formula I plus j, and then like square or cube or whatever you need to do to that -1. You guys are good at that. So if we're going to do, this is the same matrix as before, so we really should get the determinant as 1 again, but this time we're going to use a cofactor expansion, and we're going to go down column 3. Okay, so we're going to go down this column. That means the determinant of A, we will start with A13. Now the column 3 is what's going to be the same. C13 plus A23 C23 plus A33 C33. Okay, so expanding that out, we have A13, which is 0, and I know that that will make the whole term 0, but I'm just going to keep going just so we can see the whole expansion. And then the cofactor will be -1 to the 1 plus 3 times the determinant of A13. Okay, then A23 will be 2 times -1 to the 2 plus 3 times the determinant of A23. And finally, A33 is 1 times -1 to the 3 plus 3 times the determinant of A33. Okay, so we already know the first term is 0. 2 plus 3 is 5, which means this is going to be negative, so -2. The determinant of A23, a second row, third column, will be 1, 2, 2, 0. And then 3 plus 3 is 6, which makes that even, which makes this plus the 1 times the determinant of A33, 3, 3, so 1, 3, 2, -1. That looks like a 7. Sorry. -1. Okay. All right. Last step. -2. 1 times 0 is 0 minus 4 plus 1 times -1 minus 6. It's getting late. Okay, I've got 8 minus 7 equals 1, and that is perfect because that's what we got last time. Okay. Now, this was not super useful here because we have a 3 by 3 matrix. We already know what the determinant was. It was way easy for us to just think about it the old way. But this cofactor expansion could help us in a matrix like this, where we have a whole nice column of zeros right here. Which means if I do a cofactor, if I try to find the determinant of A, and I do a cofactor expansion down column 1 instead of doing across row 1, that means that I'm going to have a lot of terms that will just be multiplied by 0. So I'm going to write out the whole formula, and so we can all see it. So the determinant of A, down column 1, and I'm making this choice. Notice nobody told me to make this choice. Okay, this is where you get to have the power and do what is easiest for you. So A11, C11, plus A21, again I'm doing down column 1, so the column is staying the same, the row is changing, C21, plus A31, C31, plus A41, C41. So A11 is 1, and then I'm taking negative 1 to the 1 plus 1 times the determinant of A11, which will be a 3 by 3 determinant. Okay, but then A2 is 0, A21 is 0, A31 is 0, A41 is 0. Great, so we just turned a 4 by 4 determinant into really a 3 by 3 determinant multiplied by 1. So we're just looking for the determinant of A11, which is, if we eliminate the first column and the first row, 2, 0, 0, 1, 2, 3, 5, 1, 5, and you can do this however you would like. Let's do it the multivariable calculus way. So I have 2 times 10, 2 times 10 minus 3 minus 1 times, magic, 0, because this will be 0 and 0, plus 5 times, look at that, 0 and 0. That made that really easy. All right, 2 times 7 is 14, and that is the determinant of our 4 by 4 matrix. And that made that, choosing that column made a lot of that work super easy. And then even here, if we had done another cofactor expansion, I would have just gone down probably column 1 again, because then I would have really realized that all of these would have been 0. And I could have just done 2 times the determinant of this teeny matrix down here. This leads us to the last page. Something really nice about certain shapes of matrices. So if we have an upper triangular, which we've already been talking about with our LU factorization, we have an upper triangular and lower triangular matrices. If A is a triangular matrix, either upper or lower, okay, and that has to be that it has all zeros below the diagonal or above the diagonal, then the determinant is just going to be the product of the main diagonal entries. Okay, so we're going to prove that just in one case here, but you could prove it in all cases. And notice here, the notation, the note I left you is that this is in, instead of being in brackets, this is in the straight line, so that means they want me to take the determinant. So the determinant, and we're going to go down, we could also go across row 4, or down column 2, down column 1, that starts with a 2. So the determinant of A, I'm going to go down column 1, is 2 times negative 1 to the 1 plus 1, because I'm in times the determinant of A11, okay, because this is A11. But then as I go down, all of my other A21, A31, A41 are all 0, so I don't have to find any of those. So that means I'm looking for 2 times the determinant of A11, which is 1, 0, 0, 2, negative 3, 0, and 3, 5, 4. Okay, so I'm multiplying 2 times 1 times negative 3, so negative 12 minus 0, minus 2 times 0 minus 0, plus 3 times 0 minus 0. So again, I ended up only multiplying these two numbers. Those were the most important. And I multiplied them by 1. And I multiplied that 1 by 2, which was all the entries along the diagonal. So this gives me negative 24. Oops, sorry, negative 24, which is, again, if I had multiplied down the diagonal, 2 times 1 times negative 3 times 4, negative 24. Okay, so one other easy way to find a determinant, but again, this only works for upper or lower triangular matrices. It's because we have all of those zeros in the lower bound or the upper bound that really make taking the determinant easier. Okay, so that's how we take a determinant in something bigger than a 3 by 3 matrix, or even a 2 by 2 matrix, because we can use this for 3 by 3.